Welcome to this lecture series in real analysis. In this lecture, we'll discuss the algebra of derivatives, meaning suppose we have two functions whose derivatives we know, what about the sum of those functions, what about the product of those functions, and so on. All we need to know is the connection between derivatives and limits. So we defined derivatives as the slope of tangents, and we defined tangents in a geometric fashion. So there is a connection between the limit definition or the limit criterion and the definition that we gave. In textbooks, the derivatives are defined by limits, so there is no connection to be made. Anyway, so we'll just use the formula that the right derivative, if it exists at a point A of a function defined on an interval, not necessarily an interval really, we don't necessarily demand that the function is defined on an interval, but I, for simplicity, keep it an interval. So fine. There are some constraints that we need on the domain of the function, like we don't want the domain to be rational numbers. So if the domain is an open set, that is good enough. Anyway, so suppose f is a function defined on an interval, a is a point which is not the right boundary point, then the right derivative of the function f at the point a, if it exists, is same as this right limit. So this is basically what we need, and the two-sided version is just remove this subscript, remove the plus. I have written it here, I don't know why I rewrote it. And we need to know about the algebra of limits. So if we have two functions f and g, and suppose the limit of f as x approaches a exists, and similarly for g, then we have a statement about the limit of the sum. So those things, I don't want to recall all of that. So with that, let us proceed. Here are some problems for practice. And now let us get started. So first we will discuss derivatives of sums, the simplest. Fix two functions f and g, and suppose a is a point in the domain. Again, the domain is an interval, and a is not the right boundary point of it. Then if f and g are right differentiable at a, same is true for f plus g, and the right derivative of the sum at the point a is the sum of the right derivatives. Alright. So very simple, it is just a straightforward exercise in algebra of limits. So we need to show that this limit this right limit exists and is equal to that. So just use the definition of the sum. Shuffling the terms in the numerator. We have that, and now we distribute the denominator. And now we know this limit, the limit of this as x approaches a from the right, and same for this exists. Therefore, this exists, and in fact, the limit just distributes. So this expression is same as and that's it. This is equal to the right derivative of f at a. This is equal to the right derivative of g at a. All right. Very straightforward, but also very useful. Now for the derivative of products. Same hypothesis. F and g are functions defined on an interval, and and a is not the right boundary point. If we assume that f and g are right differentiable at a, then same is true for the product function, and in fact one can compute this right derivative via the following formula. So it's not just simply the product of the right derivatives of f and g, it is a little bit more complicated. But if you try to, prove it, this formula automatically comes about. And that's what we are going to do. So we are concerned with this limit, which is equal to that expression. And now we do a little trick in the numerator. Yeah, so what should we do? GA. So if I subtract fx times GA and add it, I should get something. So I subtract fx times GA and add it back. So it doesn't change the numerator. And the denominator is what it was, which is x minus a. So this is equal to that expression. And now again, I will just distribute it and take the limits. But there is a small subtlety here, so I will do it in full. Yeah. So this thing has a limit as x approaches a. GA is just a real number, and since f is right differentiable at the point a, this thing has a limit. So the second term clearly has a limit as x approaches a from the right. This guy has a limit as x approaches a from the right because g is also assumed to be right differentiable at a. What about that? This is not just some number. This is varying with x. But remember, right differentiability implies right continuity. So f is right continuous at the point a, and hence this also has a limit at the point. This also has a right limit at the point a, and the right limit is equal to the function value. That's what continuity means, or that's a consequence of the definition of the of the definition of continuity and the definition of limits. So therefore, this also has a limit. This has a limit, that has a limit, therefore the product has a limit. And therefore, this expression that we have written becomes this thing multiplied by that's what it becomes. But this is f of a, that is the right derivative of g at a. This is the right derivative of f at a. So this becomes f of a times the right derivative of g at a plus ga times the right derivative of f at a, and that's it. That's the formula for the derivative of the product. Very nice. Now for the inverses. So fix a function defined on an interval, a be a point in the interval which is not the right boundary point, and also assume that f does not vanish anywhere in its domain, so that the inverse, the reciprocal, or whatever you want to call it, this function is well defined. So we claim that the reciprocal function, so if f is right differentiable at a, then the reciprocal function is also right differentiable at a, and its derivative at the point a can be calculated via this formula. Strange looking formula, but yeah, it's also pretty straightforward. So we are concerned with this limit. We want to show this limit exists and is equal to that number. Okay, but by definition, that's what it is. That's the definition of 1 by f of x. Right? So this is equal to what? This is equal to Just did some algebra. Okay, I'll take a minus sign outside. And I'll also take 1 upon f of a outside. So when we are taking limits, scalars don't matter. Minus 1 is just a number, fa is just a number, we can pull them out. And this expression is well defined because f of a is non-zero. We have assumed that f doesn't vanish anywhere in the interval. So I'll just pull out 1 upon or minus 1 upon f of a to get and now again this thing has a limit as x goes to a from the right. Let me put a bracket. Yeah. So this thing has a limit as x goes to a from the right, and same is true for this. Why? F being right differentiable implies f is continuous, and then we use the algebra of continuity. The limit of the reciprocal function is the reciprocal of the limit. And since f again is not vanishing anywhere in its domain, all of this is meaningful. So we just use our knowledge of limits. This becomes the product of those two limits. And the first limit is the right derivative of f at a. The second is just 1 upon f of a. And that gives us the correct answer. So let me leave it to you to fill the details. There's nothing really left. All right, so we have this thing out of the way. And now for derivatives of quotients. Fix two functions, f and g. Again, they are defined on intervals, the same hypothesis. This time what we have is the function g does not vanish anywhere on the interval, so that this ratio is well defined. And if we assume f and g are right differentiable at the point a, we want to show that this ratio, which is well defined, is also right differentiable at a. And the derivative of the ratio, the right derivative of the ratio at the point a, assumes this formula. So the proof of it is just write f upon g as f times 1 by g. We know the right derivative of this, we know the right derivative of that. And once we have product of two functions whose right derivatives we know, we can just use our formula for the product. So that's it. Just apply the formula here, you will get that. So I'll leave this one as an exercise and move on. So now we use what we've learned to compute derivatives of polynomials. We'll start with the simplest example. We have the identity function, fx equals x for all x. What is the derivative of it at any point? So we are just concerned with this limit. This time we are working with the two-sided version because we really only care about the two-sided version, most of the times anyway. So at the point a, this is the limit that we care about. And yeah, so everything that I said so far has a left-sided version and a two-sided version. All of that I leave to you to figure out and prove. All right, so this limit is what? By definition of f, this is x minus a upon x minus a, which is equal to 1. So the derivative of this function at every point is 1. The derivative is constant. Fine, not such a big deal. What about the nth power function? So this function is the 1th power function. If you put n as 1, you recover the previous guy. So what about this function? What is its derivative? Okay, let's talk about the squared function. So for n equals 2, let's first discuss that. So f is anyway f. Take g as f. We are defining g is the same as f. So what about the derivative of f times, what is f times g? The product fg is then, sorry, I don't want to do this. F is already the squared function. We already have that, and now take, let capital F and capital G both be equal to f. Both be equal to the identity function, not f, identity function. So the identity function is that one. So now what is f times g? Capital F times capital G is nothing but the function f. This will square whatever is fed to it. If you feed x to capital F, you get x. You feed x to capital G, you get x. And those things are multiplied. So what you're getting is the squaring function. Okay. So what about its derivative? So we know that the derivative of the product at any point A is given by this formula. And we know the derivative is constant and is equal to 1. The derivative of the identity function is 1. And the function by definition is the identity function. So f of a is capital A, and similarly for that. So this is equal to 2 times a. So the derivative of f at any point x is twice of x. Alright, let me do one more. What about the cubed function? So here we have fx equals x cubed for all x. This time, let capital F be the squaring function and capital G as the identity function. And now apply the product business. Thus, let me change the color maybe. So what we have is f times g is again little f. Just check. And therefore, the derivative of f times g at x by the same formula is this expression, which is a squared times 1 plus g of a is a. What is f prime a? F prime a is the derivative of the squared function, but we just computed it. So it turns out this is equal to 2 times a, and hence we have a square plus 2a square, which is equal to 3a square. So the derivative of the cubed function is that, in other words, we can write f prime x is equal to 3x square for all x. And you can continue. You can just execute this process inductively, and you will end up with the following fact that the derivative of the nth power function, the one that we have written over here for an arbitrary n, the derivative of f is given by that formula. Just an inductive application of what we just did. Okay. Now what about a polynomial? So fix n real numbers, sorry, not n plus 1 real numbers, and define this function which takes x to that expression. Such a thing is called a polynomial. I'm sure we visited this before. What about the derivative of this? Well, we know the derivative of the individual things, right? The derivative of this is 0 because that is a constant function. This is just a1, the derivative of this we know, and so on and so on. So what is the derivative of p? The derivative of p at any point is going to be a1 plus 2a2 plus 3a3x, is it? Sorry, it was 2a2x plus 3a3x square, and so on up until we are just using the fact that the derivative of sum is sum of derivatives, and the derivative of scaled function, so we didn't explicitly prove the scaling result, but it's trivial. So all I'm saying is that the derivative of scaled function, what am I writing? The derivative of the scaled function at any point, let me scale by lambda, at any point a is lambda times the derivative of the function. That's all I'm using. And you can see this by the product rule. Just take the constant function lambda as one of your functions. Its derivative is 0, and hence the product rule gives you this. So I'm using that implicitly here. So we know how to differentiate polynomials. Okay. And finally, let's take an example. This time we do not have a polynomial but a rational function. Such a thing is called a rational function. It is a ratio of two polynomials. It is meaningfully defined over all real numbers because it doesn't, the denominator doesn't vanish anywhere. Let's compute its derivative at the point 1. So we'll just use the formula. So define capital F as the numerator and capital G as the denominator. Okay, so then we are interested in the derivative of this at the point 1, and we know this is given by this formula, which is, so what is capital G of 1? It is equal to 2. F prime 1 is 3 into 1 square plus 0. I'm skipping a lot of steps. What is the derivative of capital F at 1? It is a polynomial and we are differentiating a polynomial. So at any x, the derivative is this. At 1, therefore, the derivative becomes that. And then minus, what is f of 1? F of 1 is 4. And g prime 1 is 2 times 1 plus 0. Divided by g of 1 square. G of 1 is again 2 and we are squaring it. So that's our answer. Let me compute it. So this is 2 times 3 minus 4 times 2 divided by 4. 6 minus 8 by 4, which is minus half. So that's your answer. You can do this exercise for an arbitrary x. It will be a cumbersome expression. Alright, so that's all I wanted to say. As usual, like, comment, share, subscribe, and I will see you next time.